International Software Testing Qualifications Board ISTQB Foundation Level Specialist Syllabus Performance Testing provided by American Software Testing Qualifications Board and German Testing Board. Read to you by Gameel. Chapter 1 Basic Concepts 1.1 Principles of Performance Testing. Performance efficiency, or simply performance, is an essential part of providing a good experience for users when they use their applications on a variety of fixed and mobile platforms. Performance testing plays a critical role in establishing acceptable quality levels for the end user and is often closely integrated with other disciplines such as usability engineering and performance engineering. Additionally, evaluation of functional suitability, usability, and other quality characteristics under conditions of load, such as during execution of a performance test, may reveal load-specific issues which impact those characteristics. Performance testing is not limited to the web-based domain where the end user is the focus. It is also relevant to different application domains with a variety of system architectures, such as classic client-server, distributed, and embedded. Technically, performance efficiency is categorized in the ISO 25010, ISO 25000 product quality model as a non-functional quality characteristic with the three sub-characteristics described below. Proper focus and prioritization depends on the risks assessed and the needs of the various stakeholders. Test results analysis may identify other areas of risk that need to be addressed. Time behavior. Generally, the evaluation of time behavior is the most common performance testing objective. This aspect of performance testing examines the ability of a component or system to respond to user or system inputs within a specified time and under specified conditions. Measurements of time behavior may vary from the end-to-end time taken by the system to responding to user input, to the number of CPU cycles required by a software component to execute a particular task. Resource utilization. If the availability of system resources is identified as a risk, the utilization of those resources, e.g., the allocation of limited RAM, may be investigated by conducting specific performance tests. Capacity. If issues of system behavior at the required capacity limits of the system, e.g., numbers of users or volumes of data, is identified as a risk, performance tests may be conducted to evaluate the suitability of the system architecture. Performance testing often takes the form of experimentation, which enables measurement and analysis of specific system parameters to take place. These may be conducted iteratively in support of system analysis, design, and implementation to enable architectural decisions to be made and to help shape stakeholder expectations. The following performance testing principles are particularly relevant. Tests must be aligned to the defined expectations of different stakeholder groups, in particular users, system designers, and operations staff. The tests must be reproducible. Statistically identical results, within a specified tolerance, must be obtained by repeating the tests on an unchanged system. The tests must yield results that are both understandable and can be readily compared to stakeholder expectations. The tests can be conducted where resources allow, either on complete or partial systems or test environments that are representative of the production system. The tests must be practically affordable and executable within the time frame set by the project. Books by Molineux and Microsoft provide a solid background to the principles and practical aspects of performance testing. All three of the above quality subcharacteristics will impact the ability of the system under test (SUT) to scale. 1.2 Types of performance testing. Different types of performance testing can be defined. Each of these may be applicable to a given project depending on the objectives of the test. Performance testing. Performance testing is an umbrella term including any kind of testing focused on performance, responsiveness of the system or component under different volumes of load. Load testing. Load testing focuses on the ability of a system to handle increasing levels of anticipated realistic loads resulting from transaction requests generated by controlled numbers of concurrent users or processes. Stress testing. Stress testing focuses on the ability of a system or component to handle peak loads that are at or beyond the limits of its anticipated or specified workloads. Stress testing is also used to evaluate a system's ability to handle reduced availability of resources, such as accessible computing capacity, available bandwidth, and memory. Scalability testing. Scalability testing focuses on the ability of a system to meet future efficiency requirements, which may be beyond those currently required. The objective of these tests is to determine the system's ability to grow, e.g., with more users, larger amounts of data stored, without violating the currently specified performance requirements or failing. Once the limits of scalability are known, threshold values can be set and monitored in production to provide a warning of problems which may be about to arise. In addition, the production environment may be adjusted with appropriate amounts of hardware. Spike testing. Spike testing focuses on the ability of a system to respond correctly to sudden bursts of peak loads and return afterwards to a steady state. Endurance testing. Endurance testing focuses on the stability of the system over a time frame specific to the system's operational context. This type of testing verifies that there are no resource capacity problems, e.g., memory leaks, database connections, thread pools, that may eventually degrade performance and/or cause failures at breaking points. Concurrency testing. Concurrency testing focuses on the impact of situations where specific actions occur simultaneously, e.g., when large numbers of users log in at the same time. Concurrency issues are notoriously difficult to find and reproduce, particularly when the problem occurs in an environment where testing has little or no control, such as production. Capacity testing. Capacity testing determines how many users and/or transactions a given system will support and still meet the stated performance objectives. These objectives may also be stated with regard to the data volumes resulting from the transactions. 1.3. Testing types in performance testing. The principal testing types used in performance testing include static testing and dynamic testing. 1.3.1. Static testing. Static testing activities are often more important for performance testing than for functional suitability testing. This is because so many critical performance defects are introduced in the architecture and design of the system. These defects can be introduced by misunderstandings or a lack of knowledge by the designers and architects. These defects can also be introduced because the requirements did not adequately capture the response time, throughput, or resource utilization targets, the expected load and usage of the system, or the constraints. Static testing activities for performance can include reviews of requirements with focus on performance aspects and risks, reviews of database schemas, entity relationship diagrams, metadata, stored procedures and queries, reviews of the system and network architecture, reviews of critical segments of the system code, e.g., complex algorithms. 1.3.2. Dynamic testing. As the system is built, dynamic performance testing should start as soon as possible. Opportunities for dynamic performance testing include during unit testing, including using profiling information to determine potential bottlenecks and dynamic analysis to evaluate resource utilization. During component integration testing across key use cases and workflows, especially when integrating different use case features or integrating with the backbone structure of a workflow. During system testing of overall end-to-end behaviors under various load conditions. During system integration testing, especially for data flows and workflows across key inter-system interfaces. In system integration testing, it is not uncommon for the user to be another system or machine, e.g., inputs from sensor inputs and other systems. During acceptance testing, to build user, customer, and operator confidence in the proper performance of the system and to fine-tune the system under real-world conditions, but generally not to find performance defects in the system. In higher test levels such as system testing and system integration testing, the use of realistic environments, data, and loads are critical for accurate results. See Chapter 4. In agile and other iterative incremental life cycles, teams should incorporate static and dynamic performance testing into early iterations rather than waiting for final iterations to address performance risks. If custom or new hardware is part of the system, early dynamic performance tests can be performed using simulators. However, it is good practice to start testing on the actual hardware as soon as possible, as simulators often do not adequately capture resource constraints and performance-related behaviors. 1.4. The concept of load generation. In order to carry out the various types of performance testing described in Section 1.2, representative system loads must be modeled, generated, and submitted to the system under test. Loads are comparable to the data inputs used for functional test cases, but differ in the following principal ways. A performance test load must represent many user inputs, not just one. A performance test load may require dedicated hardware and tools for generation. Generation of a performance test load is dependent on the absence of any functional defects in the system under test, which may impact test execution. The efficient and reliable generation of a specified load is a key success factor when conducting performance tests. There are different options for load generation. Load generation via the user interface. This may be an adequate approach if only a small number of users are to be represented and if the required numbers of software clients are available from which to enter required inputs. This approach may also be used in conjunction with functional test execution tools, but may rapidly become impractical as the numbers of users to be simulated increases. The stability of the user interface UI also represents a critical dependency. Frequent changes can impact the repeatability of performance tests and may significantly affect the maintenance costs. Testing through the UI may be the most representative approach for end-to-end tests. Load generation using crowds. This approach depends on the availability of a large number of testers who will represent real users. In crowd testing, the testers are organized such that the desired load can be generated. This may be a suitable method for testing applications that are reachable from anywhere in the world, e.g., web-based, and may involve the user generating a load from a wide range of different device types and configurations. Although this approach may enable very large numbers of users to be utilized, the load generated will not be as reproducible and precise as other options and is more complex to organize. Load generation via the Application Programming Interface (API). This approach is similar to using the UI for data entry, but uses application's API instead of the UI to simulate user interaction with the system under test. The approach is therefore less sensitive to changes, e.g. delays, in the UI and allows the transactions to be processed in the same way as they would if entered directly by a user via the UI. Dedicated scripts may be created which repeatedly call specific API routines and enable more users to be simulated compared to using UI inputs. Load generation using captured communication protocols. This approach involves capturing user interaction with the system under test at the communication protocol level and then replaying these scripts to simulate potentially very large numbers of users in a repeatable and reliable manner. This tool-based approach is described in sections 4.2.6 and 4.2.7. 1.5. Common performance efficiency failure modes and their causes. While there certainly are many different performance failure modes that can be found during dynamic testing, the following are some examples of common failures, including system crashes, along with typical causes. Slow response under all load levels. In some cases, response is unacceptable regardless of load. This may be caused by underlying performance issues, including but not limited to bad database design or implementation, network latency, and other background loads. Such issues can be identified during functional and usability testing, not just performance testing, so test analysts should keep an eye open for them and report them. Slow response under moderate to heavy load levels. In some cases, response degrades unacceptably with moderate to heavy load, even when such loads are entirely within normal, expected, allowed ranges. Underlying defects include saturation of one or more resources and varying background loads. Degraded response over time. In some cases, response degrades gradually or severely over time. Underlying causes include memory leaks, disk fragmentation, increasing network load over time, growth of the file repository, and unexpected database growth. Inadequate or graceless error handling under heavy or over-limit load. In some cases, response time is acceptable, but error handling degrades at high and beyond limit load levels. Underlying defects include insufficient resource pools, undersized queues and stacks, and too rapid timeout settings. Specific examples of the general types of failures listed above include a web-based application that provides information about a company's services does not respond to user requests within 7 seconds. A general industry rule of thumb: the performance efficiency of the system cannot be achieved under specific load conditions. A system crashes or is unable to respond to user inputs when subjected to a sudden large number of user requests, e.g., ticket sales for a major sporting event. The capacity of the system to handle this number of users is inadequate. System response is significantly degraded when users submit requests for large amounts of data. E.g., a large and important report is posted on a website for download. The capacity of the system to handle the generated data volumes is insufficient. Batch processing is unable to complete before online processing is needed. The execution time of the batch processes is insufficient for the time period allowed. A real-time system runs out of RAM when parallel processes generate large demands for dynamic memory which cannot be released in time. The RAM is not dimensioned adequately, or requests for RAM are not adequately prioritized. A real-time system component A, which supplies inputs to real-time system component B, is unable to calculate updates at the required rate. The overall system fails to respond in time and may fail. Code modules in component A must be evaluated and modified. Performance profiling, to ensure that the required update rates can be achieved. Chapter 1 ends.